Okay, it's recording now. Okay, I think we can get started. So welcome everybody to this third session of the RVFPGA micro-credential that started some weeks ago. And today we'll analyze the input-output at a low level. So if you remember from last week, we were analyzing the input-output of the RVFPGA SoC for some peripherals. It was LEDs, switches, and 7-segment displays, but at a high level, meaning that we're just communicating and interacting with those peripherals from our program by writing and reading the registers, the memory mapped registers, and well, doing different functions in our programs to communicate and to handle the peripheral. So today we want to go to a low level and analyze the very low code of a specific controller in the SoC, which is the 7-segment displays controller. And we want to analyze, understand it, and then modify it to provide a new functionality. Okay. Let me go to the GitHub. This is the part for this week and today. This is the work you were supposed to do during this week, and this is the work to do today. Everything is described in detail in this directory module 2B. But before going into that directory, let me mention that in the module 2, because module 2 is about input-output, and it's the first part, which we were working in last week, and the second part, which is today's work. So the first part, which was module 2, called module 2 here in the GitHub, recommended you to view this video about input-output, which includes not only what we did last week about high-level input-output, but also some explanation about the low-level details of the 7-segment displays controller. So I just want to remind you that you should, if you haven't, or if you want to review it again, remember that that part is explained in this video. Okay, so you can go there and view it again in case you need to remember some things about the controller. Okay, let me go back to the main web page, and then let's go into module 2B, which is for today's work. We told you to do some work before today. It was mainly two tasks. One was to try to understand the 7 displays controller in Verilog, which I'm going to do now a brief explanation. It's explained in the video, as I was mentioning, and also some details are given here. You can find more information in the internet, several places. So you have lots of information for helping you understand the controller. This was the first task. The second one was to install Vivado. Vivado works in Windows and in Ubuntu and in Linux systems. You can choose whatever you want. The thing is, it's quite big, time-consuming, the installation, as you've probably experienced. And we need Vivado in order to resynthesize the bit stream for the system on chip. After we make some changes to the controller, as specified in the exercises below. Let me see, there's somebody trying to join. Pau?
Yes, it's just a question.
Yes.
We have had some issues
Sorry.
with Vivado installation, and I'm wondering if it's necessary to have it.
Well, yes, it is necessary, at least that you can access some Vivado. If you want to share your colleagues' laptop, if you're working close to some other people who was able to install Vivado and you want to share it, it's okay. But you need to use Vivado for synthesizing the new SOC. Unless you unless you work with Vidbo Simulator, which is another option. I mean, ideally you will do the work on the board, because I think it's better. No, it's real. But if you cannot access Vivado in your own laptop or some colleagues' laptop, it's also okay to work in Vidbo. Okay, but remember that in Vidbo, as in Vivado, what you have to do for the SOC, for regenerating the bit stream in Vivado, you have to do the same in Vidbo. The provided binary for the simulator does not include the changes, obviously, in the 7-segment controller. So you have to modify it exactly the same you do for the board, and then recompile, in this case, the binary for the simulator.
All right. Thank you.
Yeah. Okay. So if you can use Vivado, use it and use the board. If you cannot, for different reasons, you cannot use yours or some colleagues' Vivado, you can work on the simulator. Okay. Okay. So I was saying these are the two tasks you should have done before today's session. If you haven't been able to finish any of those, you can work on them now. Then, once you finish these two tasks, you are asked to do this exercise. Well, it's divided in two exercises, but it's in fact one exercise, which is modify the controller and use it in a program. Okay, so modification of the controller is first exercise. It explains what you have to do. I'll go in some details now. Then second exercise is to use the new controller. Note that in the original controller, you cannot write something like this. Why is that? Because you cannot write, for example, an L, because the controller does not support that digit. Okay, the original controller provided in the SOC can only show one of the 16 hexadecimal digits from 0 to 9, A, B, C, D, E, and F. And that's it. You cannot do nothing else than that. In the modified controller, we want to be able to show any combination of LEDs. So we could show some other letters that were not allowed in the original controllers, or we could even show any combination, even though it's meaningless. For example, I could switch on this LED and this LED. It doesn't mean anything for us, but the controller allows us to do that. So after modifying the controller, you'll be able to write something like this, hello. Okay? Okay, let's go back to the first task, and let me open the slides for the video explaining the controller, the one provided in module 2. Okay, let me go back there to make it clear. Module 2, this is the input-output video that you watched some last week, and that it contains some details about the low-level details of the controller. And it provides these slides, which I'm going to open now. Here they are. So specifically, we're interested in this part, okay, explaining the 7-segment displays. The last day I didn't go in detail here. Let me go in detail now. Let me present. Okay, so the connection of the 8 digits 7-segment displays on the board is explained in this slide, and this is the first thing you have to understand. You have more details if you look for the board, the board documentation on the internet. You will find details about how the connection of the 7-segment displays is done in this board. Okay, the 7-segment displays are these elements that we have here, and which can also be used in the VideoIntroModule simulator. The thing is, there is a common anode. The anode controls if the digit is on or off. So there's a signal called AN0, which controls if this digit is on or off. These signals work at a low level. So when they are low, it means when AN0 is equal to 0, it means that the digit is on, okay? And they are low assertive. Instead, when AN0 is 1, the digit will be off, okay? So each of these 8 signals controls individually each of the 8 digits that we have on the board. So if, for example, I write 1 1 1 1 0 0 0 0, these 4 digits will be on, these 4 digits will be off. That's for the common anode signal. Now, the cathodes are individual to each display. So there's a cathode that controls this LED, this LED, which is called CA. It's here, CA, signal CA, will control this LED for the 8 digits. So if I write CA equal to 0, this LED and this one, and this one, and this one, and this, and this, and this, and this will be on. If I write a 1, they will be off. Similarly, cathode B controls all 8 digits which are in this position. So this, and so forth. When that signal is equal, 1-bit signal is equal to 0, they will be on. When that signal is equal to 1, they will be off. Okay, is this clear? Do you all understand this? How the physical connection is done on the board for this peripheral? Any question? It is important that you first understand the physical connection. No questions? Okay, so let's continue. Now that we understand how the physical connection on the board is for this peripheral, we need to provide a hardware that understands that connection and that lets the processor or the core run a program to control that peripheral. The core will control the peripheral through memory mapped input-output, as we know. This peripheral will have registers mapped to specific addresses that in fact, you already used last week, and that we can write from the core, okay? But it's different, the registers that we write from the core and the signals that are used physically in the peripheral. And we have to transform the information from the registers to the information of these signals that will control the peripheral. And we do that inside the 7-segment displays controller. Let me go back to the system-on-chip figure that we had, so that we saw some days ago. It's okay. Okay, yeah, this one. We have the system on chip. This is the core, the EH1 core that we are using in our course. These are the buses. Remember, we have an AXI bus and a wishbone bus and a bridge that connects those two buses. And then we have different controllers connected to the different peripherals that we have in our system. And specifically, we have the system controller which connects with the 7-segment displays. So this controller will translate the information that we provide from the core to the memory mapped registers to the signals that control the peripheral. And it has to understand perfectly how this is connected and how the core will provide the information. And it's different. Those two things are different. The core will provide its information through two registers that we used last day, enables register and digits register. And this controller has to transform that information into the cathodes and anodes that I've just explained. So any question? This is the concept of how all this is connected in the system, okay? And this can apply to any other controller. The hardware controller has the task of understanding how the peripheral is connected and understanding how the core provides the information and transform between those two worlds that are different and that the hardware controller must know. Is this clear? Okay. Okay, so going back to the 7-segment displays controller that we were talking about, okay, we now know the physical connection, and we know from last day that the core will write two registers to control this peripheral, enables register and digits register. And you already use that in your programs. You know that the enables register allows us to switch on or off each of the 8 digits. And we know that the digits reg provides, let me go to that slide, the digits reg provides the information to show in each of the digits through a 32-bit register where each 4 digits correspond to one different digit. Each 4 bits correspond to each of the 8 digits that we have on the board. So for example, digit 0 is a 4-bit signal that controls the value to show in this digit. Digit 1 will be a 4-bit value controlling the value to show in this digit, and so forth. And the enables register, which is low assertive, will control if each of the digits is on or off through 8 bits. Okay? Any question? Now, our interest today is this module, this 7-seg displays controller, this black box here that we want to go into and that we want to understand and modify. Okay, the 7-segment displays controller that will transform the information from these two registers into these two signals that control physically the digits. Okay, remember that the information to write on the registers comes from the core through the AXI and wishbone buses, etc. Okay, that is already explained. But our interest today is this box. Okay. Now, let me ask you. Let's see if you can. Well, maybe you've already seen this. In that case, you can answer, or maybe you haven't seen that, but you can guess what you think. How do you think the controller will have to behave in order to be able to provide to the peripheral this information in the way it's needed, as described in this slide? Can any of you answer that? How is the hardware controller supposed to work in order to provide information to the peripheral? What do you think? No. Nobody? I need to transform the information from the two registers into the signals needed by the physical peripheral. What does the hardware controller need to do for that, taking into account how the peripheral is connected in the board? Any idea? No ideas? So the idea is that we're going to provide a hardware that iterates through the 8 digits, meaning that it will switch on each digit individually. So it will first switch on this digit, then it will switch on this one, then this one, then this one, till the end. And then it will go back to the first, second, third, eighth one, and then it will go back to the first, and so forth. And that will happen forever. Okay, it will be iterating through the 8 digits. Now, when this digit is on, the hardware will provide through the cathodes the value to show in this digit. When the second digit is on, the cathodes will provide the value to show in the second digit, which can be different to the first one. But given that the cathodes are common to all the 8 digits, I need to do something like what I'm describing. I need to do first this one, then this one with its value, then the third one with its value, and so forth. And then go back again to the first one and iterate forever. That way, the human eye will not detect that I'm doing this one at a time. But if I do it fast enough, the human eye will assume that they are all on with their individual values and will not detect that it's going one by one. Do you understand the idea? Note that this is needed due to the way the peripheral is connected on the board. If it was connected in a different way, then we need a different hardware controller. That's why the hardware controllers are specific to the peripheral that they are using, and they know how to communicate with that specific peripheral. If I have a different 7-segment displays connected in a different way, I will need to change the hardware controller to connect to them. Okay, understood? Any question? As I said, this is explained in the video I mentioned before, so you can go back to the explanation if you need to. Also, I will share this video later, so you can also view this again. Okay. Finally, now that we understand how the physical connection is, how the 2 registers work from the core, how the hardware controller transforms those 2 registers into the physical peripheral, how it works, now we want to see how this is programmed in Verilog. Okay, this is part of your job, but I'm going to help you a bit with the following explanation. So let me now open the Verilog module for the 7-segment displays controller. Well, it's the system controller. This is the module, system controller, and it has different things, and it has several different things. One of them is the 7-segment displays controller. It has some other things, but we don't care about those. We just care now about the 7-segment displays controller. If we go down, we find this part where we are decoding the address coming from the core. Why is this necessary? Because the core can write to different positions in memory, meaning different things. Part of them are the main memory, part of them are the LEDs, part are the switches, part of them will be any other controller that our SOC has, and some of them, this part, are the registers controlling the 7-segment displays. And this value, 14 and 15, are the least significant bits of the address generated by the core. And if they are exactly 14 and 15, I am trying to communicate with the 7-segment displays. And specifically, the first one, 14, is the enables reg. So when I'm writing something to this register, I'm controlling if the digits in the 7-segment displays controller are on or off. When I'm writing information to this address, I'm controlling what I want to show on each of the digits. So this part is important because it lets us understand how the core is writing to the memory map registers controlling the 7-segment displays. Now, the main part here for us is at the end of the file. This is the instantiation of the 7-segment displays controller, which is implemented right below. It's implemented here, 7-segment displays controller. This controller, if we go back to the slides, is this box. This box is this module here, which goes till the end of this part. This is the 7-segment displays controller, the hardware controller that we were showing in the slides. So first of all, what are the inputs and outputs to the module? Well, we already know from this figure that the inputs are the enables register and the digits register. Here they are. Enables register, 8-bit signal controlling the if each digit is on or off, and digits register controlling the value to show in each of the 8 registers. Well, also we have the clock and the reset that, of course, and it's not shown in the figure. Then we have 2 outputs. One is the AN signal, AN0, AN1, 8-bit signals, 8-bit signal here. And the other one is this CACB, which is called differently, but it's exactly the same. It's called in an array called digits bits. It has 7 digits, which correspond to CA, CB, CC, and so forth. Okay, so these are the 2 inputs and 2 outputs of the hardware controller, which are illustrated in this figure, or if we go up, in this figure, the 7-segment displays control. Okay, any question about this? All clear? Sorry. Okay. Now, what happens in the module? The module has to do what I described before. It has to iterate through the different digits and provide the value to show in each digit in each iteration. Okay. So it will implement different hardware modules. It will implement a counter. Why is that? Because we need to iterate with a period. We need to stay for some nanoseconds or microseconds in the first digit and show the value. Then we need to go to the second digit and show a value, then to the third, and so forth. So we use a hardware counter for that purpose. Okay. I left for you the details about how this counter is implemented. You can look at that on your own, then ask me if you have questions, but I don't explain that now. We also have 2 multiplexers, one for the enable signals. Here, it receives the, sorry, this multiplexer, which is a 8-to-1 multiplexer, will receive the 8 possible enables that it will have. Note that the first one is only the first digit is on. The second one, only the second digit is on. The third one, only the third digit is on, and so forth. And as an output, it will transform that to the AN signal required by the physical peripheral. So when we're in the first iteration, in the first digit, we're only switching on the first digit. When we go to the second one, we're switching on the second digit, and so forth till the 8th digit. And then we're going back again and do the same process again. So this multiplexer will control the enable signals. The second multiplexer will control the cathodes or the digit signals, the value to show in each digit. And we need to use a decoder here. And why is that? Well, this is because the value that we're receiving from the core is encoded differently than the value that we have to show in the cathodes. So let me go back to the slides now. So when I want to show, let me go to this one. When I want to show a 1 in a digit, I need to switch on segments B and C. That's the value I have to provide through the cathodes signal. However, the core will not give me a 1 here or a 0 or whatever value this has and whatever value this one has. The core will give me this encoded in hexadecimal, in binary. So this, from the core, I will receive a 0001, which is the value of 1 encoded in binary. However, the peripheral needs me to tell the controller to provide a cathode, a value of 0 here that will switch on this segment, and a value of 0 here which will switch on this segment, and a value of 1 for all the other segments. And that's a different encoding than the one I'm receiving from the core. I don't know if this is clear. Let me explain it maybe here. What I was trying to explain is that the value in the digits reg is not the same as the value that we need to provide to the cathodes. It's encoded differently. The value here is encoded in binary. The value here is meaning which of the LEDs needs to be on and which one needs to be off. So we need a transformation, a decoding from this signal into these signals. And that is provided in this 7-segment decoder. Well, you can look at that in more detail, more slowly, and you will understand. Finally, the multiplexer will provide the value to show in each period. So when I'm switching on the first digit, this will provide the value to show in the first digit through the cathodes. When I'm in the second period, it will provide the value to show in the second digit, and so forth until the 8th digit. More or less, this would close the explanation. This would be all for what you need to understand for the hardware controller. If you understand the hardware controller, you are ready to modify it. Once you modify it, you can generate the new bit stream or binary if you're working with a simulator, and use the peripheral as provided in the extension of the control. Okay. So the first exercise today is to let me go back to the module 2B. The first exercise is to modify the controller, as I already explained before, in order to provide any combination of LEDs, not only those for the hexadecimal digits, but any other combination I want. That way, I'll be able to show things like an L, for example, which I cannot show in the original peripheral. So you need to perform changes to this file in order to modify the controller and be able to show any combination. Okay. Let me say also here that a project is provided that you can use in the RVFPGA trace simulator that is very useful to debug hardware programs, very low programs. Maybe you already have used in your work a a similar simulator to this that allows you to analyze internal signals of the hardware. In the course, we're using the RVFPGA trace simulator, and you're provided with this project that is specific for the 7-segment displays. And it allows you to visualize the internal signals of the hardware controller that I've just explained, the 7-segment displays controller. Look, in this simulation, you have the enables register and digits registers, which are the inputs to the controller, and you have the anode and the cathode signals, which are the output of the controller. And you can visualize them in time and see how they change in order to achieve the functionality that we've described. So this can be useful to help you understand the peripheral and also later to debug the peripheral, because when you make changes, probably they won't work at the beginning. If they don't work, you can visualize the signals and what's happening in RVFPGA trace to help you debug the hardware. Probably you're used to doing these things in your work at OpenChip or whatever else you are working at. If you're working in hardware design, you are probably used to use these kind of tools in order to simulate and debug the hardware. So this is the one we're using here, and you are provided with this project that will help you understanding the controller and debugging it. Okay? And then the second exercise, once you have created the bit stream or the binary for the new controller, you want to use it. And you're going to use it and make a program that writes hello in the 7-segment displays. Okay? Once you have modified the controller and it's working with the extension, you will be able to show something like this. Hello. Okay? So, any question? Okay, this is the work to do today. If you haven't finished the previous work that was supposed to do in the previous sessions, you can also work on that. You can ask me questions about the work for today or the previous work. I will be here for the whole session and answering your questions. If you need to review the previous tasks to do, you can do also that now. And now it's time for you to work. As the other days, I'll stay here, but now you work on the tasks. And by 12:30 or 1, I will explain the work to do for next session. Okay? So, any question? Okay. Time to work now. I'll be here. If you need to ask anything, please say it or write it on the chat. Thank you very much.